Hello everyone, I'm Vaibhav Gupta, and in this video, we'll go over an example to gain more familiarity with TensorFlow and understand its process. We'll take an example of image classification where we'll understand how to classify cats or dogs from the images. We'll build an image classifier using the TensorFlow, and we'll be using the Keras API as it is much easier and faster to develop deep learning models using Keras. And we'll also be using the keras.sequential model to define all our layers in its constructor, as you will see later in this video. With this, I hope that we all will get some practical experience and develop intuition for first building data pipelines using image data generator class of Keras. We should the second understanding the importance of training data set and how to identify problems like overfitting and how we can prevent it. Third, some techniques like data augmentation and dropout to prevent or fight problems like overfitting in the computer vision tasks. So let's go over the tutorial. It follows a basic machine learning flow where first we'll examine and understand the data. Second, we'll build an input pipeline. Third, we'll build the model. Fourth, we'll train the model. Fifth, we'll test the model. Sixth, we'll improve the model and repeat the process. Let's start by importing the required packages. We are importing the as required TensorFlow package and required Keras models, layers, and image data generator class. The OS package is required to read the files and data structure. NumPy is used to convert Python list to NumPy array and to perform required matrix operations. And then we'll be using the matplotlib to plot the graphs and display images in our training and validation data. Second, let's begin by downloading the dataset. For this, we are using the cats versus dogs dataset from the Kaggle, which has around 25,000 images of dogs and cats. So basically, this is the URL to download the filtered dataset from there. So we'll download the data, and from .get file, the data gets downloaded to our directory, and we'll save the path to this directory at our path variable. The dataset will have the following data structure. It will have a train folder, it will have a test, it will have a validation folder. In the train, we'll have the cats dataset, we'll have the dogs dataset. Similarly, in the validation folder, we'll have the cats dataset and we have the dogs dataset. So as we can see, our data downloading process is complete. Now we'll assign the variables to the location of the training and the validation directory. Then we'll assign the variables to the path of the cats and dogs in the validation directory and cats and the dogs in the training directory. Now with this, let's understand the data. Let's see how many cats and dogs images are there in the validation and the training directory. After running this snippet, it shows that we have total of 1,000 training cat images, total of 1,000 training dog images, total of 500 validation cat images and 500 validation dog images, giving us a total of 2,000 images in our training set and 1,000 images in our validation set. Before the data preparation step, let's define our variables which we'll be using to pre-process the training data set and then train the network. In this example, we are keeping the batch size of 128. The number of cycles or the passes in the training set will be around 15, which is our apex. And the image height will be 150 and the image width will be 150. So let's prepare that. This step is done. Yeah. So let's prepare our data. Let's go for the data preparation step. We have to format the data into appropriate pre-processed floating point tensors. So before feeding the network, so for that, we have to read the images from the disk. We have to decode the contents of these images and convert into the proper grid format as per their RGB content. when we talk about the images and when we decode the images into more of a grid or a matrix format, where each cell of the matrix correspond to each pixel. We can either decode in the RGB format, which is red, green, blue, or we can go for the HSW, which is hue saturation value. So in this example, we are going for the RGB format. So each cell of the grid corresponds to each pixel of the image, and each cell has three values. Each value for either for first for the R, then for the green, and then for the blue. And each value ranges from 0 to 255, which defines the intensity of that color. So 0 means that it has zero intensity of red. 255 means it has the max intensity of red. After converting into the RGB content, we'll then convert the image that we have decoded into the floating point tensors. And then we'll rescale the tensors from the value of 0 to 25 to the value of 0 to 1, as the neural networks prefer to deal with the smaller input values. But fortunately, as the image data generator class from the Keras, it performs all these tasks for us. It reads the images from the disk, pre-processes them into proper tensors, and it will also set up the generators that convert these images into the batches of tensors, which will be helpful while training the network. So now we'll use the image data generator class, and we are rescaling it from the value of 0 to 1. After that is done, we'll be using the flow from directory method to load the images from the disk. And then we'll be applying the rescaling and resizing of the images into required dimensions. We'll be using this for the both first, the training data generation, as we have done like 2000 images belonging to the two classes. And then we'll be doing it for the validation data generation. After performing this step, let's visualize our training data set. So we'll take the batch size, and we'll plot 5 images from them using the matplot library. In this, I'm using the next function. It returns a batch from the data set. The return value of the next function is form of the training feature and the training image and its label. Since now we are just visualizing the image, will not be concentrating on the label, and we'll be just seeing what the image looks like. And here we have defined the function to plot the images of the figure size 20 by 20. So if I run this, now the function is defined, and if we see the sample training images of five training images, we'll see this is our training set of cats. Mostly here we can see the cats. After we have visualized the data, we have prepared the data, it's time to create our model. In this example, we are creating the model, which consists of 3 convolutional blocks with a max pool layer in each of them. There's a fully connected layer at the end with 512 units on the top of it. All these layers are activated by the rectified linear unit function. Why? Because it's much cheaper to compute this function, as its function is linear for all the positive values and 0 for the all negative values. It's sparsely activated, since it's 0 for the all negative values, it's not going to activate for those values, so it's only going to activate for the positive values. And third, it is converging faster in our case. So let's create our model. After the model is generated, we'll combine the model using the Adam optimizer and binary cross entropy function. Adam optimizer is adaptive moment estimation, which is basically a adaptive learning rate optimizer, which is designed to specifically training the deep neural networks instead of the classical stochastic gradient descent algorithm. With this, we use this algorithm because of its better performance and speed. Along with this, for our loss function, we are using the binary cross entropy function, which is more of a binary logarithmic loss function. We use this cross entropy function when there are only two label classes, 0 or 1. And in this case, we have cats or dogs. So with these parameters, we have now generated our model. To summarize and to see our model summary, we'll see our convolutional layers, our dense layer, and yes, as you can see these outputs. Now it's time to train the model. We will be using the fit generator method of the image data generator class to train the network model. And it will run for 15 steps, as we have defined our epoch as 15. I think each step, yes, each step takes around, I guess, let's see how much it's taking in this example. Yes, it takes around 8 to 7 seconds, and it will go for around 15 steps. So in total, it will take around 1.5 to 2 minutes to complete this process. So let's resume after the training of the model is completed. So step 14 of 15 is running. Now we are at the step 15, the last step. Now we have trained the model and it's complete. As we can see here that the loss and the accuracy of the training data set, as well as the loss and the accuracy of the validations data set has been, are the outputs. Let's visualize these losses in the form of the graph. Here we can use the history function to get the accuracy and the the validation accuracy, to get the loss and the validation loss. And our axis will be the number of steps that we have run. So let's plot this graph and see what our output is. Okay, so as you can see here that the training, for the training accuracy, the accuracy increases, but for the validation, the accuracy increases till the 70%, and it gets stabilized at around 70-75%. Similarly, for the loss, if you see the training loss, it's decreasing continuously. But for the validation, for our validation training set, it's way far from what we have achieved for our training data, from our training set, and our validation set stabilizes at around 60%. Let's understand what went wrong, and we'll try to increase the overall performance of the model. As we discussed, like the training accuracy is increasing linearly over the time, whereas the validation accuracy stalls around 70%. And there's a big difference between the accuracy of training and validation. It's a sign of a phenomenon called overfitting. When there are small number of training examples, the model sometimes learns from the noises or unwanted details, which we can get from the training examples. It can learn and modify its models in such a way that it negatively impacts the performance of our model. And this phenomena is what we term as overfitting. It means that this model will have a difficult time generalizing on a new data set. So how do we prevent this? How do we prevent overfitting? So we'll be discussing two of the ways to prevent overfitting. One is called the data augmentation, and the another is called the dropout. Let's understand what the data augmentation is. As we discussed, like the overfitting generally occurs when there are small number of training examples, uh, which forces the model to learn from the noises and unwanted details. One way to fix this problem is to augment the data set so that it has sufficient number of training examples. So now we have to take an approach of generating more training data from the existing training samples by augmenting the samples using some random transformations that still yield the believable looking images. While doing the augmentation, we have to remember one thing, that our goal should be in such a way that our model should not see the exact same picture twice during the twice during the training. as it will defeat the purpose of the training. So how do we do that? If we can increase the number of types of images in our training set, we'll be able to more expose our model to have better aspects of data and to generalize the model for the new data set better. We'll try to apply some transformation, mainly the random transformation using the image data generator class of the TensorFlow keras, where we'll use the transformation like horizontal flip, zoom, etc. So let's see how we do that. First, we'll apply the horizontal flip. It's pretty easy to apply the horizontal flip. We just have to pass the parameter of horizontal flip and set it to true in our image data generator class. Now with this, we have defined the image generator with the horizontal flip. Now with the flow from directory, we'll take a batch size and we'll apply on a set of a training data. Let's apply the horizontal flip randomly for the 5 times on one image and see and visualize it further to see how it's affecting our image. Now, as you can see that these images are pretty similar looking, and they are more believable on the terms of cat. It's not changing the core purpose. The image is still of a cat, but we have horizontally flipped the image. Now the next thing we can do is we can randomly rotate the image, let's say to around 45 degree. So with this, how do we do that? We'll pass the parameter of rotation range in image data generator and we'll set it to the 45 degree. So yeah, now we have created an image generator with the 45 degree rotation, which are applied to the images randomly. With this, we'll take a batch of a training data set, we'll apply the rotation range on the training data set, and then we'll look at a different augmentation on 45 images. Let's see how it looks. As you can see, the image of the cat, for example, the image third, image fifth, they are rotated of around 45 degree. They can be on the either side of the axis and they are randomly selected. As still it's not changing our image as a whole, it's still the image of the class of the cat. And we are just trying to increase our data set by introducing more type of unique images. The third example that we can take is zoom augmentation, where we'll try to zoom our images to 50%. It can range from 0% to 100%. We have taken the example with 50%. So let's again try it on the training data set generator and let's see how the image looks like. So you can see that some images are being zoomed. It messes with the aspect ratio of the image, but still the image core purpose that it's an image of a cat and the label should be the cat is still there. So we have to introduce more type of different images to increase our training data set and to make it more diverse, but at the same time we are yielding the believable looking images. So as we have seen the 3 different data augmentation techniques, we can apply more data augmentation technique like width shift range, our height shift range, and so on to give more diversity to our training data set. So let's put it all together and we'll randomly apply the rescaling, the rotation, as we discussed, the width shift range, the height shift range, the horizontal flip, and the zoom range, and we'll create an image generator for that. And as we have created the image generator, let's apply this operation on the training data set. And let's see out let's apply all this operation on one image 5 times and let's see the output. It's very important to analyze each and every step while we are dealing with image processing, just to make sure that we are not worsening our images while we are creating the training data set, as it can uh, have the counter effect on our validation, and it can, instead of increasing our accuracy, it can result in decreasing our accuracy. So as we can see in our output that some of the images are zoomed as well as rotated or horizontal flipped, but still the images are, it's the process is yielding the believable images, believable looking images, and we can use these images to in this example, as is in this example, we can use this image to for the label of dog very clear, very easily. So we have create the generator for the training data set, but for the validation data set, we'll not be applying all these data augmentation techniques. That those techniques will only be applied to the training examples. For the validation data set, we'll only be applying the rescaling um, of 0 to 25 RGB to 0 to 1, as to as it is very easier to handle smaller inputs in our neural network. So uh, we'll just apply that and create the validation data set. Now with this, let's create a new network with the, okay. Before going forward, we have discussed about the data augmentation. The second technique that we can do to prevent overfitting are the dropouts. The dropouts is a form of regularization that forces the weights in the network to take only small values, which makes the distribution of the weight values more regular, and the network can reduce the overfitting on smaller training examples. What I'm saying is, in the dropout is kind of a regularization technique in which we apply dropout to a layer where it randomly drops out number of output units from the applied layer during the training. For let's say we can define dropout as 0.1, 0.2, 0.6, which means that we are dropping out 10%, 20%, or 40% of the output layers or the neurons randomly from the applied layers while we are training our model. So as we discussed that the dropouts randomly kills 10 or 20% of the output units, it helps us to regularize our model, and it helps us to force the weights in our networks to take only smaller values. So let's understand with an example. Here we are applying dropout to the first and last max pool layer, where we have randomly set the dropout, where we are saying that around 20% of the neurons will be randomly setting the 20% of our neurons to 0 during our each training set. As a part of our regularization, it will help us to avoid overfitting in our training data set. Let's create a new network with the dropouts. It's created, and then we'll compile our new model with the same optimizer as we used earlier in the same binary cross entropy loss function. Now it's time to train our model with the new, now train our training data set with the new model. At this time, I think it will take around 14 to 15 seconds for each step, and will be, and our cycle size is around 15 steps. So it will take around 3 to 4 minutes to complete this whole training. We'll resume once after the training completes. So 2 more iterations are left, and once it will be done, we'll try to analyze the training and the new training and validation accuracy and loss, and hopefully it should, with our changes, the model should improve. Okay. Yeah. So the step is complete. Let's visualize it again with the same axis of the range of our epochs, which is 0 to 15. And let's see how our new training model performed. As you can see in this example, the training accuracy and the validation accuracy increases coincides with each other, and now the gap has decreased. In fact, for this model, our validation accuracy is more than our training accuracy after the eighth or ninth iteration, which signifies that this model is performing better than the model that we trained earlier. Similarly, if you see the graph of training and validation loss, our validation loss of training and our loss of training and validation both decreases with a similar pattern, and there is very much less gap between the training and the validation. With so this graph clearly signifies that this model is performing better with significantly less overfitting than before. The accuracy of the model should go up after training the model for more epochs, but as we can see the clear signs that um, we have improved our model just by data augmentation and dropouts. So before summarizing, I'll try to go over the example again, and we'll conclude on what we have done. So first, we import the packages which were required. We imported the TensorFlow, the Keras models, layers, image data generator, and we imported the required packages of NumPy, Matplot library, and OS. Then we downloaded the data from the Kaggle, and we assigned the path to the new downloaded path to the path of the new downloaded directory. So as we know that our data set should look something like this. Then we assigned our variables to the training directory path, to the validation directory path, to the cats and the dogs in the training directory path and the validation directory path. Then we first analyze the data, and we analyze how many training data set we have and how much validation data set we have. Then we defined our own parameters for pre-processing. These parameters changes with each example. And the one way to define this parameter is by analyzing what type of data you have, and and by like learning and experience on when you try to build more new models, you will be able to see which type of which type of pre-processing variables work better for which type of examples. Once we have defined these pre-processing variables, we can change and play with these variables and see whether our model is improving or not. After that, we'll prepare our data, where we understand that we have to convert this into the floating point tensors. And so first we decoded the image in the grid format of RGB, and then we rescaled it to 0 to 25 using the image data generator class. And then from the flow, with the flow from directive, we applied that generator to the training data to the training data um, in the with each in the form of batches. And then we apply the same operation on the validation data set. We have seen that it shows there are 10,000 images of the validation data set belonging to two classes. Here we only have two classes of cats and dogs. If the complexity increases, our loss function changes when we have more classes. But since we are just trying to get familiar with the TensorFlow, we have taken a basic example to understand the image classification. Then we visualize the training images. It's very important to, at each step, to visualize the image, whatever training image you have in the image processing, to understand the whether you'll be able to get the desired output. Then we created the model. We defined our optimizer. We defined our loss function, and then we trained our model. And we saw that in the first model, the model was suffering the problem of overfitting. And once we see some phenomena like this, we have techniques like data augmentation, dropouts. Sometimes people, they normalize the image, they standardize the image. numerous techniques, and these techniques, they really depends on what type of data you are handling with. In this example of animals, the horizontal flip, the rotation works better. But if you are working with something like ID cards um, or documents, sometimes techniques like binarization or thresholding to filter out some noise performs much more better. So to understand which type of augmentation technique you have to understand your training data set and experiment on which type of, after applying which technique, the training data set looks better to you. So as we have discussed earlier, that we applied horizontal flip, then we applied randomly, then we randomly rotated the images for of at from the axis of 45 degrees. Then we applied augmentation, and we applied width shift, and we apply height shift, and we put it to all together with this rescaling on the all training images. And these augmentation techniques are applied randomly to each image. But we just make sure that you don't apply it to the validation data set, because we don't want to change the validation data set. We are changing the training data set just to decrease the decrease the phenomena of unwanted noises, to prevent the overfitting. But we don't want to change anything from the validation data set. So our validation data set, we are just applying the rescaling of 0 to 25 to 0 to 1. Then as we discussed, that we applied one more technique called dropouts, where we will be assigning the value of 0 to some percentage of the neurons in our first layer, in our last layer. This helps us to make our network more generalized and more flexible to the new data set. And it decreases the rigidity, and makes it more regularized. So after the dropout, we created a new model. We applied the same optimizer and the same loss function. Since we have only 2 classes, we are using the binary cross entropy, but with the increase of the classes, we might have to explore new loss functions. And then we train the model again. After training the model, we see when we visualize that, we see that our performance has improved with significant decrease in the overfitting. So now we have segregated one phenomena, and we can focus on what other ways we can improve the accuracy. Are we getting the right kind of images? Is it because of the pixelation in the images, or the quality of the images, or is it because of or is it because of the layer that we have formed in the sequential constructor? So now we can go over and improve those factors, and the accuracy, and also the accuracy should improve as we have more epochs. So with this, we have seen a basic example of image classification in TensorFlow. With the more videos in the future, we'll go into more complex examples, and we'll go into more details on how to execute those examples. With this summary, I'll end this video. Thank you.